This animated diagram outlines the standard autonomy loop currently dominating open-source development. A text prompt enters a black box LLM, a large language model, and the model outputs a raw, mutated system command directly to a target, like a production database. There are no intermediary checks. When a model hallucinated in a chat window, you got a bad poem. When an agent hallucinates with direct system access, it executes unconstrained mutations. The model invents a parameter, the command runs, and the target database crashes. The AI industry has reacted to this risk by proposing a strict binary. They assume operators must choose between speed-first, highly dynamic systems that execute quickly, or locked-down, restricted systems that sacrifice capability for safety. That assumption misidentifies the root vulnerability. The problem is not the intelligence or the reasoning capacity of the model itself. The vulnerability is the complete lack of control plane rigor surrounding the model's outputs. Simply patching these open loops with better prompts will not survive enterprise production. Deploying agents at scale requires altering the core architecture to formalize a hard boundary between the model's reasoning and the machine's execution. That boundary is what PRISM provides. PRISM is an agent runtime built entirely around a constitutional operations plane, where every single action is evaluated against policy rules before it ever reaches a host system. This typographic layout presents the exact equation driving PRISM's architecture. Governed autonomy plus causal observability equals safe scaling. To understand how PRISM controls non-deterministic models, we need to deconstruct its architecture from first principles, examining how it intercepts commands, how it isolates environments, and extracts tool contracts. Features like persistent terminal virtualization and multi-agent swarms require high levels of system access. To deploy them in business environments without collapsing the host network, they must be restrained by NIST-compliant governance. NIST refers to the National Institute of Standards and Technology, which publishes rigorous frameworks for managing AI system risks. This diagram shows the PRISM runtime control flow pipeline. PRISM operates on one cardinal engineering rule: tool execution is never detached from policy evaluation. Looking closely at Step 2, you can see how the policy engine intercepts every request. It classifies the risk and action constraints immediately, mapping the requested command into a strict 3-tier authority matrix. Tier 1 handles autonomous, low-risk operations. If an agent wants to list the files in a directory or read a text document, the read-only command passes directly through the Tier 1 gate without human intervention. Tier 3 handles high-risk operations. If an agent hallucinates or decides to execute a destructive command, like deleting a server directory, the system halts the packet at the Tier 3 gate. It cannot execute until a human operator explicitly approves it. Standard agent frameworks often treat safety as an afterthought, building loose guardrails around the model itself. PRISM enforces safety at the infrastructure level, treating the model as an untrusted client. When a Tier 3 operation is denied, or if the approval window times out, PRISM does not crash. Approval denied and timeout are programmed into the workflow as expected operational states. The orchestrator triggers predefined fallback routes and rollback semantics to recover cleanly. Deterministic governance gates are the mandatory buffer. They are the exact mechanism that allows non-deterministic models to safely operate within live production environments. This abstract visualization illustrates the technical danger of terminal access. Granting an LLM persistent, stateful shell access to a host operating system allows localized errors to mutate and compound rapidly across the network. This state machine diagram details PRISM's virtualization solution. Instead of giving the model direct access, PRISM forces isolated shell sessions into a strictly tracked lifecycle, beginning here as it transitions from idle to active. During the executing phase, an autonomous command might hang, or the agent might accidentally trigger an infinite loop. When that happens, the session exceeds its time budget and automatically drops into a timeout state. To regain control, PRISM initiates a strict signal escalation protocol. It attempts a graceful shutdown first. If the process refuses to terminate, it escalates to a forceful kill signal, completely terminating the session and locking it into a revoked state. Every single state change and every forced termination requires the system to log a specific reason code. This creates a fully auditable trail detailing exactly why an agent was stopped. Without the ability to cleanly revoke access at any microsecond, system autonomy is a liability. The infrastructure must be able to sever the connection instantly without corrupting the host machine. To manage external tools, PRISM enforces the discipline of treating them as precision agent computer interfaces, or ACI. ACI are strict, typed contracts that define exactly how an AI is allowed to interact with a specific application, rather than relying on loose API wrappers. This diagram illustrates the dynamic staging pipeline. When an agent attempts to load an unverified plugin, the raw code enters the system, and PRISM extracts its schema map. PRISM extracts the tool's contract either by reading its direct manifest or by introspecting its TypeScript decorators, special markers in the source code that define function structures. It maps out the exact inputs, outputs, and mutability flags. From that extracted contract, the system calculates a risk score based on the tool's capabilities. It then auto-assigns the tool to the appropriate policy tier. High-risk tools are automatically routed to the Tier 3 approval queue. By forcing all dynamic capabilities through a strict baseline comparison, the system neutralizes the threat of compromised third-party code. If the contract doesn't match the safety baseline, the tool never loads. This strict control answers a core enterprise liability question. When an autonomous agent mutates a production database, who is legally responsible for that action? PRISM answers this with Character Accountability Control, or SAC. As seen in this diagram, every session starts with 4 distinct data blocks: the AI character profile, the registered platform user, the human operator, and the software client. PRISM forces an identity binding. It snaps these 4 variables together into a single accountability chain, explicitly linking the digital agent's actions to the human operator authorizing the session. Before any activity event is logged to the database, a cryptographic sealing process occurs. A SHA-256 algorithm sweeps over the chain. SHA-256 is a cryptographic hashing function that generates a fixed size, unique, and irreversible signature for a given piece of data. This locks the event, outputting an immutable hash. Because these hashes are permanently fixed, engineers can achieve deterministic replay. They can pull the exact parameters of a past incident and reconstruct the trace, step by step, with zero ambiguity. If an agent tech system lacks this level of cryptographic causal observability, it cannot be audited. Without an audit trail, it is entirely unsuited for deployment in regulated enterprise environments. Because PRISM's fundamental operations are consistently governed, the system can safely scale. It can expand into complex multi-agent orchestration without amplifying operational risk. When a prompt enters the system, a fast classifier model analyzes the intent. Instead of attempting to answer directly, it routes the task to specialized subagents, like a dedicated coder or summarizer. This graph demonstrates swarm orchestration topologies. Agents can be organized into a mesh layout where all nodes communicate peer-to-peer to reach a consensus, or they can use a star layout where a single central coordinator delegates subtasks to multiple worker agents. For chained refinement, PRISM uses sequential topologies. A pipeline layout hands data from A to B to C. A broadcast layout takes a single prompt and distributes it identically to all agents to evaluate parallel solutions. Despite the autonomy of these swarms, every individual subagent remains inextricably bound by the core 3-tier policy engine. They cannot bypass the gates. High-end capability is not achieved by querying a single massive model. It is achieved by orchestrating a governed swarm of right-sized agents working in concert. PRISM offers a dual-profile contract, PRISM Individual and PRISM Business, running on the same core engine. Individual optimizes for velocity with permissive default gates. Business overlays mandatory compliance rules, strict approval workflows, and exhaustive audit logs. Regardless of the profile, the actual operational capability surface, the terminals, the dynamic tools, the multi-agent swarms, remains identical across both. Organizations no longer have to build 2 separate platforms to satisfy the conflicting demands of ambitious developers and strict compliance officers. We are approaching a shift in enterprise AI procurement. The criteria for evaluating autonomous systems is moving from benchmark scores to operational accountability. This image shows a PRISM workspace directory, backed by SQLite. SQLite is a lightweight, file-based database used to store persistent records locally. Future enterprise deployments will demand cryptographic proof from systems like this. They will require hard evidence of who authorized an action, why it ran, exactly what changed, and how to roll it back. This irrefutable foundation allows PRISM to safely test advanced mechanics, like constitutional causal compilers that validate architectural plans before execution, and dual-lens memory arbitration that weighs the semantic relevance of a memory against its operational risk. The strategic value of an agentic system is no longer measured merely by what it can do. It is measured by what it can irrefutably prove it did.